Hi and welcome to my electricity lesson, my first lesson on electricity, and I must say I find electricity fascinating. It is definitely a topic that I think everyone can understand, but it can get a little bit tricky to explain some of these concepts, so I hope I do well. First of all, let me start by a definition of what is electricity. Electricity, you might just say, well, it's what causes my lights to work. But electricity technically is the flow of electrons. The flow of electrons. So you might recall if you watched any of my chemistry lessons, or if you have any idea about chemistry, that all elements and all things are made up of elements, and elements are made up of smaller particles called atom, and an atom consists of a nucleus, which in it has particles called neutrons, which are neutral particles, and protons, which are positive particles. Now, these particles are absolutely fixed. They can't move. They are part of that element in that substance permanently. But what we then also have is what we call the electron cloud. Let me just draw in the electron cloud. The electron cloud is a space around the nucleus of an atom, and in that electron cloud we find particles called electrons. Now, electrons are free to move. They can be shared among atoms, can share electrons, and that's the whole study of chemistry, is actually how atoms share their electrons. And electricity follows from the fact that some compounds can actually allow their electrons to move from one atom to another, and they then share their electrons among one another in a fluid way, and these are called metallic bonds. Metals have the ability to let their electrons flow among one another, and the metal that's most successful at this is copper. So copper, that's the unit copper, and that's why whenever you open any electric component, you will find copper wiring in there. And then other elements are also definitely used, but copper by far is the most conductive material, allowing its electrons to move the most freely. Now, in order to explain the concepts of electricity best, I like to use the image of a water tank. Now, the reason I like to use water is because the same principles that guide the flow of water, like we're looking at the flow of electrons, the principles in mechanics that guide the flow of water also affect the principles in electricity, the flow of electrons. Let me just fix that, the flow of electrons. So, the first thing that we will need in physics terms is we'll actually need something that can flow, okay, like a fluid. So that is necessary in order to have something to flow out of this pipe. Now, in electricity, that is going to mean we need a conductive material. In other words, something that allows for particles to flow, and in this case, and in this illustration, we'll need a fluid, okay? And in that same sense, we don't need necessarily a chemical fluid to allow for the flow of electrons, but we definitely need a material that allows its electrons to flow, and copper is therefore a good example. The second thing that we'll need is, in order for water to flow, if it wasn't for this pipe, okay, water wouldn't flow. It will just stay in this container. Okay, so one thing that we need is a source. For the water to flow in here, we will need a source of the flowable material, and we'll also need an outlet. Even if we have a place where the water is coming in, but there's no place for it to go out, we will still not have the flow of electrons. So we need a source and an outlet, and that will come from the battery. Okay, the battery, that will be the source. A battery is just one source and outlet for electrons, and we'll look at each one of these more in depth. Okay, the source and outlet for electrons, and then thirdly, you will notice that when we do have this flow, and let's change color a little bit, when we do have this flow in here, the particles will have a certain velocity. Now we'll measure that velocity with unit per time. Okay, so how many units pass a certain point per time? So for example, when you do have a current flow, like a river or something flowing, the way they would do it is they would say liters per hour. Okay, in other words, a unit, or gallons per minute, or some sort of a volume unit that they would use with water per some sort of time unit. In electricity, we call this current. Okay, and current represents coulomb per second. Don't worry if you understand it now, but coulomb is a unit in electricity. It is a number, it's a group of electrons. A whole team of electrons together is called a coulomb, but it's a specific number of electrons, so it works very good. Current is therefore the velocity at which it flows, but this velocity depends on a few things, and I'll explain that again using the illustration. You see, the velocity in this pipe here, the beginning, final velocity, and an initial velocity will be the same. Now initially, when we just open the tap, if there's nothing in the pipe, then yes, initial velocity will be 0 because it's just starting to flow, and final velocity will now depend on this height. Okay, so final velocity will depend on the height, and I think it's something like the square root of initial velocity plus 2 times height times gravity. I think something like that. No, I'm forgetting my square there. Okay, something like that. It's not very important, but I want to show you is initial velocity is going to be 0 anyway, so that one's going to fall away. The gravitational constant is going to be a constant, so the only thing that can really affect the velocity here at the end is height. Okay, how high this thing is. Okay, now height is not so much to do with the actual length of this, but actually it's got to do with the fact that in the beginning we have some sort of potential energy, and in the end we have some sort of potential energy, and the initial potential energy is mass times gravity times height. The final potential energy is mass times gravity times height. So what we see is that the height in the end is less than the height in the beginning, and because of that, the potential energy in the beginning is less than the is more than the potential energy in the end. But we know that energy cannot be created or destroyed, only converted from one form to another form. So what happened to my energy? It was converted into kinetic energy. In other words, the energy that it has, the velocity, the current that obviously kinetic energy will describe the current. The current is affected by the difference between these two potential energies, and that is called potential difference, or another word for it is voltage. Voltage is the potential difference. Now this principle still applies, and I'll look at it a little bit more in depth in a future video. Okay, potential difference is the difference between the source, the energy, the potential energy at the source, and a potential energy at the outlet. Okay, and that difference causes the water to flow. If there wasn't a difference, if the potential energy in the beginning and the end was the same, in this illustration it would be a pipe here at the top. Okay, a pipe here at the top. Since there is the potential energy in the beginning is the same as potential energy in the end, there would be no flow because there would be nothing converted into kinetic energy. Okay, the final thing that has an effect is called resistance. Okay, 5, that's resistance. Now, resistance is what the point is of electricity. Okay, it sounds like a bad thing, but it's not. It is the actual purpose of what we're doing. What resistance does is it converts the kinetic energy that the electrons have into a more useful energy. What good is moving electrons to us? It's only good if we can take that kinetic energy that electrons have and use it in a usable form like light or heat. These are different types of energy that can be created from moving electrons, which is great, okay, and the aim of that. So what resistance does is it converts, it is the obstacles in the way, the obstacles that are in the way here, that reduces the kinetic energy. Okay, so just as potential energy is converted into kinetic energy, the kinetic energy is again converted into a more useful energy like heat and light. But I'll look more at resistance, but in this example, please note that resistance will cause it's like any obstruction in this pipe. Anything that will hinder the flow of electrons would be a resistance. Okay, but just putting things in there, even though it's causing resistance, it's not necessarily converting it into a useful form. So the picture I like to use is, let's imagine there's a pipe connected here. Okay, here's a pipe connected, and on this pipe here at the end we have a little sprayer head, and it's one of those rotating sprayer heads, let's say that. Okay, and I can't draw one, but there it is. Okay, and it's spraying, and as it's spraying, it's actually rotating around. Now that is a useful form of electricity. Okay, an electric motor is an example of electricity causing something to turn, like a little electric car has an electric motor inside. It is converting the electricity, the potential electricity in the battery, into moving electrons that is then converted into by a motor into a rotation energy. And this is a good example. Why is this thing turning? There's no electricity causing a sprayer head to turn. It's the actual velocity of the particles that is causing it to turn. So hopefully this illustration just gave a good introduction and a good way of understanding electricity. After this, you'll really see, just referring back to this specific idea of mechanics and the effect that it has on the flow of water, will really help you understand electricity and how it flows in conductive materials. Thank you so very much for watching. I hope you learned something, and I'll see you in the next video where I'll look at some of these concepts a little bit more in depth and explain them. See you there.